In this video I'm going to talk about invertibility of functions. So if you've come across inverse trigonometric functions like sine to the minus 1 or arc sine, then it's going to be a similar thing to that. So I'll start by reading the definition of various different invertibility properties a function might have. So we begin with a function f from a set x to a set y, and then we have three definitions. So first of all, a left inverse to f is a function from y to x, let's call it g, with the property that when you compose g with f, so g is on the left of f, then you get the identity function on x. So this is called a left inverse if it exists, because the g is a left inverse because it appears in this composition on the left of f. On the other hand, a right inverse to f is a function, let's say h from y to x, with the property that f composed with h is the identity this time on y. And again, it's called a right inverse because in this composition here, h appears on the right of f. And finally, an inverse, or sometimes a two-sided inverse to f, is a function from y to x which fulfills both of the first two definitions. So it's both a left and a right inverse to f. So I'm now going to make a few comments on this definition before we go on to look at some examples of left and right inverses. So the first one I want to notice is that there's a little bit of symmetry in this situation. I mean, let's just take a situation where we have a function f from x to y and g from y to x, like this. Then saying that g was a left inverse to f. So g is a left inverse to f. Well, the definition is that means g composed with f is the identity on x. On the other hand, if we look at the definition of f being a right inverse to g, so translating that definition of right inverse into this case, f is a right inverse to g if and only if g composed with f equals the identity on x. Alright, so these two conditions are in fact exactly the same, and the reason I'm pointing this out is to make the observation that saying g is a left inverse to f is exactly equivalent to saying that f is a right inverse to g. Okay, let's make another comment about this, and the other comment I want to make about this definition is look at the articles we're using here. A left inverse, a right inverse, an inverse. So the reason I say a inverse and not the a left inverse and a right inverse, not the left inverse and the right inverse, is because a given function, if it has a left inverse, it may have more than one left inverse. We're going to see some examples of this. And equally, if it has a right inverse, it might have more than one right inverse. So we are actually going to see in a later video that if you have a two-sided inverse, then you can only have one two-sided inverse. But left and right inverses themselves need not be unique. Okay, a final observation before I look at some examples is just as a kind of intuition for what a left inverse is doing. A left inverse undoes what a function does, because if, let's just have a better pen here, if g is left inverse to a function f, as usual from a set x to a set y, then what this definition is telling you, just evaluating this definition at a particular element of the domain x of f, then it tells you that g of f of x equals x for any little x in big X. So that's sort of saying informally that what a left inverse G to F is doing is kind of undoing what F did. It's getting you back to where you started, which is at this element, little x. Okay, finally, let's take a look at some examples now. So we're going to see an example of a function with, we're going to look for inverses to this function. So let's take F to be the function from the real numbers to the set of non-negative real numbers, and this will have the rule f of x equals x squared. Okay, so I claim f has a right inverse, so let's define g from the codomain of f to the domain of f by g of y is the square root of y. Right, for me, square root always means the positive square root. So in this case, G is right inverse to F. And we can just check this. The fact that in order to check it, all we need to do is work out f of g of y for some y in the set of non-negative real numbers. Well, that is precisely f of root y, and since f of x is x squared, this is y again, and that's true for any y in our set of non-negative real numbers. So in other words, f composed with g is the identity on the set of non-negative real numbers, which means g is right inverse to f, and equally, as we observed above, f is left inverse to g. On the other hand, g is not a left inverse to f. Why not? Maybe pause the video and think about why not. Okay, I hope you did it. Let's just see why. I mean, one good reason is that, for example, if we take G composed with F and we evaluate that at -1, then what you've got is G of F of -1, so that's G of 1, because -1 squared is 1, and the square root of 1 is 1. Like I said, the square root symbol here always means the positive square root. So this is not where we started off with, right? We started off with -1, we ended up at 1. So G composed with F is not the identity on R. All right, that means that G is not a left inverse to F. In fact, F doesn't even have a left inverse, so it's not merely that G is not a left inverse, but F has no left inverse at all. So let's try and show that that is true. I claim that, in fact, F has no left inverse. So to see why, we'll suppose for a contradiction that H composed with F was the identity on the real numbers, so that H was a left inverse to F. Well then, on the one hand, let's work out H of F of 1. So this must be 1, because H composed with F is the identity. And since F of 1 is 1, that tells us H of 1 is equal to 1. Right, F of 1 there is 1 squared, which is 1. But let's work out something else. Let's now work out H of F of -1. Well, F of -1 is F of -1 is -1 squared, which is 1. So that's H of 1. But, again, since h composed with f is supposed to be the identity, this should also be equal to minus 1. So look what we've got here now. On the one hand, we have h of 1 is equal to 1. On the other hand, we have h of 1 is equal to minus 1. This is a contradiction. Oops. Right, h of 1 can't be two different things at the same time. So we have a contradiction. F has no left inverse. Okay, moving on. Let's look at how we actually might find some left inverses in a more kind of slightly abstract situation. So I've drawn here some diagrams which are supposed to illustrate the functions. And let's just focus on the one on the left of the picture here, where we have our function called f, which goes from the set 1, 2, 3 to the set containing a, b. And it's defined by saying that f of 1 and f of 2 are both equal to a, and f of 3 is equal to b. So I've drawn this diagram with an arrow pointing from 1 to a, and pointing from 2 to a, and pointing from 3 to b, and that's supposed to indicate where f is mapping 1 and 2 and 3. Okay, so let's try now to look for a right inverse for f. So we'll call this right inverse, which we're going to look for. We'll call it g. So g would be a function from the set AB to the set 1, 2, 3. Okay, well, I mean, we don't even know if it exists yet, but let's just think what properties g would have to have if it was going to be a right inverse to f. So what we require was that f composed with g, like this, will be the identity function on the set A, B. Okay, I think I'm just going to write ID instead of writing this subscript here because it gets a bit tricky to write. Okay, so, I mean, what does that mean? If this composition is equal to the identity function, then what we have to have is f of g of A equals A. And I also need f of g of b equals b. That's the condition for f composed with g to be the identity function on AB. Okay, so what are my possibilities for g of a and for g of a? Can you see what they should be? Pause the video and think about it. Okay, I hope you did. If f of g of a is equal to a, then whatever g of a is, f has to map that thing to a. So we should look at our definition of f and see which things it sends to a. It sends 1 and 2 to a. So we must have that g of a is 1 or 2. In fact, either of those things are possible. On the other hand, if we look at this second condition, f of g of b must be equal to b, well, the only thing that f sends to b is the number 3. So in this case, we must have that g of b equals 3. All right, so we've actually found two different possibilities for a right inverse to f. So we found two right inverses to f. So let's give them names. So g1, which we could say g1 of a is 1 and g1 of b equals 3. And the second one will be g2, defined by g2 of a is 2 and g2 of b must be 3. Okay, so this is an example of what I was talking about earlier. A function, if it has a right inverse, it may have more than one right inverse. All right, let's now move on and look at my second example on the right here, where we have a function called g, which is from the set containing 1, 2 to the set containing a, b, and c. And I've illustrated this with a diagram in the same way. So G of 1 is equal to C and G of 2 is equal to A. So this time we're going to look for left inverses for G. So look for a left inverse H of G. So again, let's just think about what properties a left inverse would have to have. It would have to have the property that H of G of 1 would have to be equal to 1. Okay, what does this say? G of 1 is equal to C, so H of C must be equal to 1. On the other hand, the other condition for H composed with G to be the identity on the set 1, 2 is that H of G of 2 must be equal to 2. So, since G of 2 is equal to A, I must have H of A is equal to 2. Okay, and those are the only two conditions which my function H has to obey in order for it to be a left inverse for G. In particular, we don't have any condition at all on where H sends the thing B. So we can in fact send B absolutely anywhere. It doesn't matter. H will still be a left inverse to G. So let's just say that, for example, the function H from A, B, C to 1, 2 defined by H of A equals 2, H of B, well, it's got to be something in 1 and 2, let's just say 1, and H of C equals 1 is a left inverse to G. Okay, but we could again produce more than one left inverse because we could have chosen H of B to be 2 instead of 1.